Yeah. But I wouldn't have 6, 7, 8, 9.
Did you have some? I can't. Oh, that's good. Yes. Okay. Okay, everybody's kind of finished. So we actually don't really have very much time. So there's only like 2 weeks, and we'll have some time to kind of review a little bit. So we're not going to do any more new physical properties because actually electroconductivity or resistivity is so important that it'll crop up into your lives. And so I want to take the next section and we're going to do electrical conductivity but with a different kind of technique. And then there's also going to be an extra little wrinkle. It turns out that the electrical conductivity has got a little bit of attributes so that it's frequency dependent. It actually depends what frequency you're trying to measure it at. And that gives rise to a survey called induced polarization. And probably for anybody who's done any mineral exploration in British Columbia or for anybody else, they have gone out into the field and done a DCIP experiment. But you've got a bit of that under your belt. And the other thing, and it's actually good news, is that all the hard part of the course is now done. So the really hardest part was actually the electromagnetics. The first hardest part, I think, was the magnetics. Even though it's really simple, it's got a lot of elements that are attached to it. And by the end of the day, if you're actually trying to kind of sketch things out as far as a profile, you kind of have to have your wits about you and be thinking about a number of things. Right? The seismic was really pretty straightforward because you can see things, you can see information going out, bouncing back. We're familiar with sound waves, and so there's a lot of things that cropped into there. And then once you do the seismic, then the GPR is just kind of like the same thing, even though that really was an electromagnetic experiment. So the main, I think, intellectual hurdle was when you get to electromagnetics, and now you've got all kinds of stuff going on. You've got time-varying magnetic fields generating electric fields inside the Earth, which give rise to currents, which give rise to other magnetic fields that you can measure. And there's a real part, and there's an imaginary part, and it's like, whoa, it's a lot of stuff. So the hard part's been done, and now what we're going to do is to go back and look at that electrical conductivity, but we're going to do it through a different technique. So what you had done before was we had a transmitter here, just a loop of current, right? And that gave rise to this time-varying magnetic field, which then generated currents, that would flow inside the Earth. Those currents gave rise to magnetic fields, and if we had, something else that could measure those fields, we could actually calculate what the electrical conductivity was. And remember, we had this formula that if the distance between these two, so if S was much less than delta, where delta was that skin depth, that we could take the ratio of this secondary field to the primary field, and I forgot exactly what we did here as far as, I don't know, there's some constants in here, but we could relate this measurement value to things that we knew and actually get out a conductivity. So that was kind of cool, right? So we have this instrument, we go along, and we're measuring a number here which we can convert to conductivity. So you're getting information by not actually sampling. So what we want to do now is the same thing, except it's going to be just a little bit different. Instead of having this loop source out here, and we sometimes refer to that as an inductive source because it's inducing currents in here, we could do the following. We could take a probe and we could hook it up to a battery or a generator, and we could have another current or another electrode here. So we take a battery, hook one end up to the earth, hook another end up to the earth. So now we've got a circuit. So it's the same kind of thing that you'd have if you had just a usual circuit. You know, you'd have some kind of a resistor, got a battery here, so we've got some kind of a current that's flowing through here. We'd have a complete circuit. We could do the same with the earth. It's just that we're kind of using this whole earth background as a big resistor. But certainly, and you could try this at home. You could take a battery, you could take two probes, and you could take a little voltmeter, or you could take a current meter, put it in there, and you find that, oh, you're actually going to get a return current. There's going to be current that's circulating through there. So if there's current that's coming through here, it's got to be a conductor. And so we could ask, like, what is the electrical conductivity? So that's what we're going to do this time. We're going to do the following. We're going to take this kind of system, hook it up to two electrodes, and we're going to call the positive electrode the A electrode, and the negative electrode the B electrode. So that's part of our circuit. And then when that happens, I mean, just kind of intuitively, the current's got to get from here to here. So, some of them might travel along here, some might travel along there. You don't exactly know how, but that's kind of the idea that you'd have. And then when you have a system like this, you could also think about taking a voltmeter and measuring a voltage someplace. And that would then give a number. And the idea is that we're going to take that number and try to convert that back to the resistivity or the conductivity of what's going on. So I want to spend just today kind of playing around with an app. And then you can be able to download this over the weekend. So if you get tired of doing a whole bunch of other things, you can kind of pull this guy up and sit down and just play and look at some images and sort of get a feeling for it. And the GPG has been just revamped, so it's a much tidier information piece now. So with the app, with the GPG, you just have a mental break from everything else and play around with some geophysics. So what do we got here? There is an outline of a sphere. We're going to ignore that for now. And we're looking at an Earth. So this is the X direction. That's the Z direction. And plotted in here is the resistivity in ohm meters. And this green indicates that it's 500 ohm meters. On the bars here, we've got an A and a B. So that's our current electrodes. So the A electrode is here at -30. The B electrode is here at 30. And there's a couple of things that we need. We need to know the rho, the resistivity of this cylinder eventually, and the rho of the half space. These things are both just at 500, so effectively we're at a half space. So that's the initial geometry. And now what we're going to do is put a current in here, and then we could look to see, okay, where are the where are the currents going to go inside the Earth? So we can plot here a number of things. We could plot the model. We could plot the potential. I'll talk a bit more about that in a second. The electric field, J, the currents, and something else that we'll talk about are the charges. And then we can have a total, a primary, or a secondary that's associated with each of these. So let's just kind of develop some intuition by doing this guy and looking at the currents. Is that clear enough to everybody? So if we take a positive electrode here, so here's our generator, and then here's the negative, you can see it's kind of like what I just sketched out there. So this is the direction of the currents. Inside the Earth, they got to go for the plus, the minus, and somehow they're just going to kind of get distributed through there. That's kind of what they look like. So now my question is, suppose I did that same thing, but now I took that sphere or cylinder. Okay, so this was sigma naught. That was like, well, it was like 500 ohm meters. So what would happen if I made this cylinder really resistive compared to the background? So let's suppose I make that 1,000 ohm meters. And I've got the currents here. What do you think would happen? Anybody?
The current would flow around the highly resistive object.
Right. So when we're talking about resistivity, it means it's hard for current to flow through. Current still wants to go from here to here, whereas before it was kind of going through like this. It's now, you might expect it to kind of go around. You probably have some that's going through, yeah. But that's sort of the kind of thing that you would expect, and we can see if that actually happens. So let's do that. So let's do the cylinder. Takes just a second to do. So if we do that, you can see that it has done that to a small extent. I can accentuate this even more by making this background region less resistive. So I'll do that. So instead of making the background 500, I'll reduce it down to 60. And now you can really see it, right? So the currents, as they're coming down, kind of flow around here and around there, and so it's definitely this is like an obstacle. And of course, what do you think is going to happen if we go the other way? So if this goes to 100, and this goes to 1,000, then what's going to happen? Yes. Thank you. It's going to flow through, right? So current that initially kind of went like this are going to be kind of sucked down. Right? I mean, that's kind of what you'd expect. And so we could do that. So we'll make that space resistive, this guy conductive. Right. So now you see how the current kind of comes down, goes across here, shunts across, and goes back up, and the same with that. Okay, so what's kind of going on here is that the current is sort of, somehow taking a path of least resistance. If there's something that's really resistive, it's going around. If it's going, if it's conductive, it's going through. So things are changing inside the Earth depending upon what the conductivity structure is. Now the question is, okay, can we measure anything? Well, the answer to that is yes, that we can. And the thing that we're going to measure is the electric potential. If I have a single current that's going in, then there's an electric potential V. You remember this from first year, I think. You've had that. If yeah, that'll work. So there's an electric potential that is related to the distance that you are from a current source, and there is a singularity such that the potential reaches a high value right at the location of that current, and then drops off as 1 upon R, so that the voltage kind of falls off as 1 upon R. And if you had a negative current that's sitting out here, then it would have a voltage that looks like this. So if I had a positive electrode and a negative electrode, then the electric potential would look something like this. And I can show you that in this next plot. So if we go back to this 500 ohm meter background, then if I have a current source here, there's an electric potential that goes up to infinity here and then falls off with 1 upon R. And I've got the negative here. And so in between, the electric potential goes as this kind of a signature. Good. Now I could go ahead and measure that, right? Because if I take a voltmeter, so just the same one as you use for your measuring the voltage of your battery. Okay, if you took that voltmeter and you just plugged it into the ground at 2 locations, you'd measure a voltage difference. And that voltage difference would be the difference between this point and that point. So in this case, you just get some number. So the question is, okay, could we take that voltage and actually turn it into a number that tells us what this resistivity is? And the answer to that, which is in the first part of the here, is given here. If I have a single current, so if I have a current I, and then I look to see what the voltage is away from that, this is equal to the resistivity of the background over 4 pi R. So if I now make my 4 electrode geometry, so here's my A electrode, and here's my B electrode, okay? If I look at some position here, M, then the voltage at this particular point here, which we call B sub M, is equal to the voltage that I get from here, which is rho I over 4 pi R. And now I'm going to subscript this with a distance, so I'm going to say that's A times M. So I'm going to keep track of all my electrodes. I've got current electrodes, and I'm going to have potential electrodes M and N. So the distance between the current electrode A and the potential electrode N is given by this. So that would be the voltage that I would get get from here. If I was going to look at a potential, at the potential that I get from at this point due to this positive current and the negative current, okay, now I've got a potential that's coming from here, and that's going to be negative because the current is negative. So it's going to be rho naught I over 4 pi r. So this is. So now I've got, at any particular point here, whatever my potential is due to these two current electrons. Unfortunately, if I measure, I mean, you'll know what happens to that. If you take your little voltmeter and you just put one into a battery, you can't get any reading. You need to make a potential difference. So what we'll do here is have the other end of the potential electrode be like this. And now here we're going to measure the voltage. So if I take this measurement here, where I take this potential difference and compute it, what that total difference voltage is, I'm just going to get some number that looks like this. So I'm going to get some number is equal to rho, the resistivity, the current, times this factor here, which is it's just a geometric factor. It's like 1 over the distance between the A and M electrode, M and N electrodes. So we just have these numbers here. So I could reformulate this into a different formulation. I could just say, I'm going to solve for rho on this side, divide by I. I'm going to call all of this stuff G, and then here's my measurement. So in the end, I'm going to measure this delta V. I know G, that's just a whole bunch of length scales. I know my current. So that actually gives me now, by rearranging this, a formula for my apparent resistivity to be equal to something here, I, G, and my delta V. So just to show what happens with this particular example, so here we've got a uniform half space of 500 ohm meters. Here's my potential. I'm going to measure the difference between these two numbers. That's my potential difference. And I'm going to convert that using that formula to an apparent resistivity. And I'm going to get 500 ohm meters, which is what this background is. So that should be enough for you to kind of go and you can take a look at this app, just play with a few things. What'll be interesting is if you make these layers a bit different conductivity or resistivities, or you do the same thing with the cylinder, and you'll take a look at what apparent resistivities that you get out, and you'll be able to start to kind of get this connection between the currents and the resultant apparent resistivities. Okay, that's good. So have a good weekend.